Deep within you, an unseen river rages, a 60,000-mile network of crimson highways carrying the very essence of life at breathtaking speeds. This is the story of the most sophisticated transport system ever conceived, a biological marvel that operates flawlessly every second of your existence. We are about to journey into this microscopic metropolis, following a single oxygen molecule from the vastness of the open air to the fiery furnace of a single cell. You will witness the elegant, brutal dance of hemoglobin, a molecular machine that defies simple explanation and has captivated scientists for centuries. And by the end, you will understand how this ancient, evolutionary masterpiece not only powers your every move, but also holds the key to future medical breakthroughs. Upon inhalation, a torrent of air rushes into the delicate, branching structures of the lungs, finally reaching the hundreds of millions of microscopic air sacs known as alveoli, a vast, shimmering internal surface that early anatomists like Andreas Vesalius could only marvel at, representing a biological frontier as unexplored as any continent. This impossibly thin alveolar capillary membrane, less than a micron thick, serves as the grand exchange point where the relentless laws of physics, governed by the pressure gradients first quantified by physiologists like August Crowe, compel oxygen to leap from the air into the bloodstream. Here, a deoxygenated red blood cell arrives, its unique biconcave disc shape, a masterpiece of evolutionary engineering, allowing it to deform and squeeze through the narrowest of capillaries, a design whose profound hydraulic efficiency is still the subject of intense biophysical modeling and debate. In a flash of biochemical genius, the iron core of its hemoglobin molecule undergoes a conformational shift, snapping shut on 4 oxygen molecules in a process of cooperative binding. A molecular ballet whose structure was painstakingly deciphered over decades by Max Perutz using the revolutionary tool of X-ray crystallography. Ejected from the heart's powerful left ventricle with a percussive force that echoes through the entire body, the newly oxygenated blood surges into the aorta, a moment that validates the foundational work of William Harvey, whose 17th-century mapping of the circulatory system shattered millennia of flawed medical dogma. This vibrant crimson torrent then cascades through a fractal-like network of branching arteries and arterioles, their thick, elastic walls pulsating in a rhythmic symphony of fluid dynamics, a complex system of pressures and flows governed by physical principles later articulated by scientists like Jean-Leonard Marie Poiseuille. Traveling at speeds approaching a meter per second, these countless red blood cells navigate turbulent junctions and bifurcations, their journey representing a logistical challenge of astronomical proportions as they deliver their precious cargo to trillions of metabolically demanding cells without fail. Furthermore, this arterial superhighway is not merely a passive conduit, but an intelligent system that actively regulates blood pressure and flow through the sophisticated mechanisms of vasoconstriction and vasodilation, a responsive feedback loop controlled by the autonomic nervous system and local chemical signals that remains a core focus of modern cardiovascular research. The frantic pace slows to a deliberate, silent procession as the red blood cells enter the vast, web-like capillary beds, microscopic vessels so incredibly narrow that the cells must deform and file through one by one, a stark visual first witnessed through the primitive microscopes of pioneers like Marcello Malpighi. It is here, in this realm of intimate contact with the body's tissues, that the lower partial pressure of oxygen in the surrounding cells creates an irresistible chemical gradient, coaxing the hemoglobin molecule to gracefully release its life-giving cargo in a precisely calibrated dissociation event described by the famous oxygen-hemoglobin dissociation curve. In addition to this simple pressure differential, the localized environment of active tissues, with its increased temperature, higher carbon dioxide levels, and lower pH, triggers a phenomenon known as the Bohr effect, a brilliant biochemical trick discovered by Christian Bohr in 1904 that enhances oxygen release exactly where it is needed most. While oxygen diffuses across the cell membrane to fuel the mitochondrial furnaces, the now unburdened red blood cell performs its second critical duty, absorbing the waste product carbon dioxide and buffering it within complex chemical systems to maintain the delicate acid-base balance essential for the entire body's survival. Now laden with metabolic waste and stripped of its vibrant, oxygenated luster, the blood begins its slow, low-pressure pilgrimage back to the heart through the venous system, a sprawling network of vessels that cleverly utilizes the gentle squeezing action of surrounding skeletal muscles and a brilliant series of one-way valves to ensure forward flow. This deoxygenated blood, often mistakenly called blue, is in fact a deep, dark maroon, its somber color a direct visual indicator of hemoglobin's conformational state, a simple yet vital diagnostic clue that has guided physicians and surgeons for centuries. The countless venules and veins gradually converge into the two great rivers of the circulatory system, the superior and inferior vena cava, which pour their contents directly into the heart's right atrium, completing a full circuit that, for an average red blood cell, takes less than 1 astonishing minute. Although this return journey lacks the high-pressure drama of the arterial surge, it is an equally miraculous feat of engineering, representing the closure of a perfect biological loop and underscoring the fundamental principle of homeostasis, the dynamic equilibrium that pioneering physiologists like Claude Bernard identified as the very definition of life itself. Understanding these intricate oxygen transport dynamics is no longer just an academic pursuit. It is the absolute frontier of modern medicine, where manipulating the oxygen-hemoglobin affinity curve could one day treat everything from sickle cell anemia to acute respiratory distress syndrome. Because we can now model these fluid dynamics with supercomputers and visualize cellular respiration in real time, scientists are on the verge of creating synthetic blood substitutes and targeted oxygen delivery systems that could revolutionize emergency medicine and organ transplantation. The simple act of breathing, once taken for granted, is now seen as the conductor of a vast biochemical orchestra, where every molecule of oxygen is a note in the symphony of consciousness, movement, and thought, a perspective that transforms our very relationship with our own bodies. Consequently, the 60,000-mile river within us is not just a plumbing system, but an information superhighway, carrying hormonal signals, immune cells, and metabolic data that collectively generate the emergent property we call being alive. You are not just a single entity, but a teeming, thriving ecosystem of trillions of cells, all supported by this silent, ceaseless, and profoundly beautiful circulatory current. Every heartbeat is a promise renewed, a powerful affirmation of a system so perfect in its design that it has sustained life against all odds for millions of years. This is the river of life, and it flows unstoppably within you.